Unmute. Mute all. All right, there. So, Cahoots. Get rid of that one and go to this one. All right. Okay. 35, 738. Someone told me it was. Some student figured out how to do cut. Somebody figured out how to do ASCII art and stuff. I don't quite know how they do it. It'd be fun to know. I don't know how Kahoot makes money, but they seem to be developing. They've been adding more music. So I guess they're not going broke. There doesn't even seem to be a pay version if you wanted to pay for it. I really don't understand how they're alive. I do have ads. Maybe they're ads. Okay. Well, anyway. All right. So I'll wait another 5 seconds. All right. So 5 questions. In key addition, what's the mathematical operation? All right, that's XOR, of course. That's what they're calling addition. It is addition mod 2. It is, but it's that's right. But XOR is equal to addition mod 2. That's how they look at it. It is. Addition mod 2, 1 plus 1 is 2, which wraps around to 0, mod 2. So addition mod 2 is the same thing as XOR. It has the same truth table. Anyway, that's why they call it that. All right. So what layer uses SBox? All right, that's the substitution. That's what the S stands for, I think. All right. Which layer has 2 sublayers? All right, the diffusion layer has 2 sublayers. All right, what processors work best when you combine the functions into lookup tables? All right, 64-bit processors, really anything longer than 8 works better that way. Not because they're multi-core, though, just because they happen to be 64-bit. But it's 64-bit is the important thing. If you wrote such a thing as a multi-core 8-bit processor, I don't think it would. But anyway, that's you're right. But I would still argue that there is one best answer. However, you're correct. And it's always a good idea to argue. So what kind of attack is useless against AES? All right. As far as anybody knows, there's no analytical attack that works. Side channel and quantum attacks can work. Side channel attacks we know work. Quantum attacks, in theory, will work when we have quantum computers. All right. So here's the winners again. Ziggy. S. Weed, who I know. And NH. I can probably figure out. All right. So there's one thing I just want to point out to you, a homework I added to your list, because it turns out to be very easy in Python, far easier than the way I used to do it. And this is the classic thing to show you the problem with using ECB mode. So if you have a picture that has lots of uniform color in it, then let me just save this thing, save image as. I'm going to put it, oh, desktop is fine. All right. So I've saved tux.bmp on my desktop. Now, just want to play this game where I can do it right here. I don't even need anything more than this right here. So from crypto import AES, let's give it a key, and it can be anything. Matter of fact, I can just use my existing key. Okay, there's my 16-byte KES. That'll do. Now, I make a cipher's new AES key. I've already done that. Okay, now, this is how you read it into a single variable. This is one of the great things about Python. With is the keyword that will automatically open the file, and then if there's a problem, it'll just close it without you having to do anything. If it does open, it'll read it binary and put it all in one variable called clear. So now I've got this thing called clear, but I didn't move to the right directory first, so let me leave. I'm going to have to set up again, cd desktop. Okay, now Python. Okay, I got to do this nonsense here. I'll use that key after all to make this easier. All right. Now, I got to do this thing to read tux into my variable. All right. So now I have this thing called clear, and I can tell that I've got it because there it is, 943,000 bytes. It's a big bitmap. You don't want to use a ping format or something for this because it mixes up the colors in a way that makes it harder to do what we're doing here. So let me just point out, in case you don't know, if you use a hex editor and view that file, on your desktop is, on my desktop, is tux. Okay. Let me just point out how this works. This is why I use the bitmap format. The bitmap has a header that's 40 or 50 bytes long that has stuff like how many colors there are, what the width is, what the height is, and stuff like that. Then it just has the colors. So this is like white over and over and over and over. I think it's 4 bytes per pixel, red, green, blue, and that's another one for alpha or something. But anyway, that's all it is. This repeating long chunk is all just one color. In some place it's going to change when it hits another color. Way down there. Yep. Anyway, so that's all it is. Oh, there we are. Yep. So see, there's a region that's different. So that's like the black line going through the white. So I wanted to show you that because the one part that might not be obvious here is you don't want to encrypt the whole file. If you encrypt the header, it's going to turn into garbage because it doesn't know what the format is. It doesn't know what the width and height is. You have to leave the first 50 or 64 bytes alone and encrypt all the rest. That's what you can do. So this would encrypt all the data in clear. So I can do this. This will create a variable called ciphertext that has encrypted the whole thing. And if you go here, you can, you got a problem, of course. Remember, everything has to be an integral multiple of 16 bytes. So what I'm going to do, I take the length of my clear, and to find out where it wraps around to 16, I'm just going to take that modulus 16. And you'll see, modulus 16, it's 2. So this thing is an integral multiple of 16 bytes plus 2. Now, for my purposes, I just want to show the effect of encrypting it, and I don't really care if I don't encrypt every single byte. So I'm going to make a trimmed variable, clear trimmed, which is going to be clear from 64 to the end minus 2. Python is great for this stuff. Now, if I take the length of that, that's now this thing, and if I take that %16, oops, gotta have 16, not 116. Okay, that's length mod of 0. So now I've taken a chunk, I've left 64 bytes at the front I'm not going to touch, and 2 bytes at the end I'm not going to touch, and I have a chunk in the middle I can encrypt that includes nothing but colored pixels, and that's an integral multiple of 16. So now I can encrypt that. So I just run this to create my ciphertext, like we've done before. And now if I do length of cipher, It's the same as the clear trims, 943,728. So now all I have to do is create a fixed image. So I take the first 64 bytes of the unencrypted stuff, add in all the encrypted stuff, and then I add the last 2 bytes. This is how you reconstruct a variable that's going to have be the right format now. So let me just put it here. It's just kind of obviously the opposite of what I did. This takes the first 64 bytes that are not encrypted, all the rest that's encrypted, and the last 2 bytes that are not encrypted to create a new file, which is going to be as big as the old one and in the right format. So that means if I look at my desktop, which will be here, I now have this thing called Tux ECB. So here's the original Tux, and here's the Tux ECB. That's encrypted. And this is why we want to talk about this. Obviously, that is not what you expect out of encryption. You can still see what it is. All this stuff that was gray just turned into green. All this black stuff just turned into that chunk. All the white turns into purple. That's what you get for electronic codebook, because each 16 bytes is just a little chunk of it here. And if the next little chunk is the same, you get the same answer. So that's why this mode is what they call textbook mode. This is what people that are learning encryption do in class, but nobody should do it in the real world. But people keep making this mistake over and over and over. Microsoft did it in 3 successive products. I know this is what was wrong with Microsoft Office encryption before Office 2007 or 2008. And it happens over and over again that they use electronic codebook mode. I've been doing Android apps. Tons of them use this mode. It's part of why I teach this class. It is amazing how many people do this, and they don't know this simple problem. And that's going to be the main topic next time, is the different modes and why you would use them. But the one you never want to use usually is electronic codebook mode. That is just there for the amateurs to begin learning to do cryptography. You shouldn't be using it in production because it has this defect. And this defect is far more serious than you might think. We were doing it a couple semesters ago in the web hacking class. This not only means that there are patterns in the output that tell you something about the input, it even means you can create valid input without decrypting stuff. You can take blocks of encrypted stuff from somebody else's web requests and just reshuffle them around and create new web requests that are valid. So you can get into things without decrypting things, with just replay attacks. That's why you've got to have a randomness, something unpredictable or random added to each byte before you encrypt it, to avoid this. Anyway, that's all I wanted to show you, I think. I'll go to the lab and help anybody who wants to work on projects down there. I'm going to stop this share. All right.